Now here we have the test results of a certain DC motor using a dynamometer, and the output of the test is this plot. The applied voltage to the motor was 100 volts. The moment of inertia of the armature of the motor is 5 kilograms times Newton times meter squared. The damping in the motor is 2. The mass moment of inertia of the load is 700, and the damping on the load axis is 800 Newton meters per second. The stall torque is 500 Newton meters here at this point, and the no load speed is 50 radians per second. And what we need here is to find the transfer function. Find the transfer function of the DC motor, which is basically G of S equals theta S divided by the input voltage EA of S, which is KT divided by RA J M divided by S times S plus 1 over J M times Cm plus KT KB divided by RA. So this is the transfer function. So I'm going to need a couple of parameters here to find this transfer function. Basically, I need KT over RA. I'm going to need this here, and I'm going to need it here. I am going to also need the KB, and I will need the mass moment of inertia, Jm, and Cm, the total damping. Okay, now I have the mass moment of inertia of the armature, and there's a mass moment of inertia here of the load. I have a gear connection here between the load and the motor. The number of teeth on these gears are 100 and 1000, so a gear ratio of 1 to 10. And so I'm gonna lump all the mass moment of inertia here. I'm gonna find Jm here, and I'm gonna find Cm at the motor. So Jm is at this axis, at the motor axis, I have Ja, the mass moment of inertia of the armature, and then I'm going to move this Jl to this axis, and I've done this before. It's Jl times the target number of teeth. The target axis is N1, the source axis is N2. I'm going to move from N2 to N1, so the target is N1, source is N2, all squared. And the same goes for the damping. Cm, the damping at the motor, is Ca plus the damping from the load, Cl, transferred from N2 to N1. So the target axis is N1, N2, all squared. So substituting Jm becomes Ja is 5 plus JL is 700 times 100 divided by 1000 squared, and that makes it 12 kilogram meter squared. And for the damping, Cm, the armature damping is 2, the load damping is 800 times 100 divided by 1000 all squared, and that would be 10 kilo Newton meter per second. So now I have these two quantities. I still need the KT divided by RA and the KB. The parameter KT divided by RA is, we found out that this is T stall divided by EA, the test voltage, the input to the motor, and KB was EA divided by omega no load. So from this plot, KT divided by RA is, the stall torque is 500 divided by the test input voltage is 100, and that's 5. KB is, the test voltage is 100 divided by omega no load is 50, and that's 2. So basically all I need to do now is substitute these values into the transfer function. G of S is KT divided by RA is 5, and further divided by Jm, so Jm is 12 divided by 12 over S times S plus 1 over J is 1 over 12, Cm is 10 plus KTRA times KB, 5 times 2, and here's my transfer function. 5 divided by 12 is 4167 divided by S times S plus 10 plus 10 is 20 divided by 12, that is 1.667. So 4 times, yeah, 1.667, and this is my transfer function. Theta output and EA input. Suppose I need the transfer function output omega of S and input EA of S. In this case, the only difference is I lose this S because this is the omega is the derivative of theta, so S goes up here, becomes omega, and the transfer function becomes 0.4167 divided by S plus 1.667, and that's a first order transfer function.